Have you ever stopped to think about the wires in your home? They snake through your walls. They hide behind your furniture. They connect all your favorite gadgets to the wall. They seem so simple, so quiet, just sitting there. But inside those seemingly boring plastic tubes, a wild and wonderful dance is happening every single second. It's a secret world, an invisible storm of energy that brings our world to life. When you flip a switch, you become the conductor of an orchestra of infinitesimally small particles, all commanded to perform a task. This invisible performance is what we call electricity, one of the most amazing phenomena in the universe. A force both everywhere and nowhere, unseen yet absolutely essential to modern life. Let's get started and illuminate the amazing science of electricity. To understand electricity, we first need to meet the star of the show, a tiny, tiny particle called the electron. Everything in the universe, the chair you're sitting on, the air you're breathing, is made of atoms, and atoms are made of even smaller parts. In the center of each atom is a nucleus, and whizzing around that nucleus are the electrons. Think of them like super tiny planets orbiting a sun. These electrons are buzzing with energy, and they don't always like to stay in one place. They are negatively charged, which is just a way of saying they have a specific kind of energy, and they are always looking for an opportunity to move. Now, in most materials, these electrons are pretty happy staying with their home atom. They are tightly bound and orbit in a predictable, orderly fashion. But in some special materials, particularly metals, the outermost electrons are a bit more rebellious. They are loosely attached to their atoms, almost like they are hanging on by a thread. These are called free electrons. They can easily be pushed or pulled away and start to drift around. It's this ability to move, to jump from one atom to the next, that makes electricity possible. Like a crowd passing a push along, not one person sprinting, but a wave of energy. So, we know that electricity is the movement of electrons. But electrons can't just move through anything. They need a special path, a kind of superhighway to travel on. These pathways are called conductors. A conductor has lots of free electrons, loosely attached and ready to move. Metals are fantastic conductors: copper, aluminum, gold, silver. Their atoms let outer electrons roam, forming a sea of electrons. That sea makes it easy to push electrons along in a current. This is why power cables are metal, most commonly copper. Copper is excellent and relatively inexpensive, ideal for wiring. Inside a power cord, you'll find shiny copper wires, the superhighway. Plug into an outlet, and voltage pushes that sea of electrons. The push gets electrons moving, electric current carrying energy. Better conductors mean less resistance and more efficient energy transfer. What about the plastic or rubber outside? That outer layer is an insulator. An insulator is the opposite of a conductor. Its electrons are tightly bound and won't move. Plastic, rubber, glass, wood. Insulators act like a guardrail on the electron superhighway. They keep current inside the copper, preventing shocks. A power cable is conductor inside for flow, insulator outside for safety. The journey of electricity doesn't begin at the wall outlet. It starts much farther away, at a power plant, a factory that generates electrical energy. They do this in many ways: burning fuel to make steam, harnessing flowing water, or capturing sunlight. No matter the method, the goal is to spin a turbine that powers a generator. Magnets spin past copper coils, pushing and pulling free electrons. That motion creates a powerful electric current, the first big push. At first, it's extremely high voltage, a very strong push. High voltage helps energy travel long distances efficiently. From the plant, power flows into a vast network of thick cables. Transmission towers are the grid's major arteries. Closer to cities, substations step voltage down, like off-ramps on the highway. Then power travels along local lines, overhead on poles or buried underground. A last transformer near your home reduces voltage to outlet levels. From there, electricity flows to your main panel and into the circuits in your walls, reaching every switch, socket, and outlet. An incredibly long journey, from giant generator to your tiny phone charger, all in the blink of an eye. Trying to imagine trillions of invisible electrons moving through a wire can be tricky. Imagine a long, clear tube filled with marbles, all touching each other. The tube is the wire. The marbles are free electrons. Push a marble into one end and one pops out the other. The push travels instantly through the packed line. That's a great way to picture electric current. A battery or outlet is like your hand pushing the new marble. It provides voltage, electrical pressure. Electrons themselves drift slowly, but the energy wave, the nudge, zips along nearly at the speed of light. That's why lights turn on almost instantly when you flip a switch, like a hose that's already full of water. Turn on the spigot and pressure pushes water out the other end immediately. Voltage is pressure. Current is flow. Wider hose, more water. Thicker wire, more current. Add sand and flow gets harder. That's resistance. Even copper has some, which turns a bit of energy into heat. That's why cords can feel warm. Electrons bump into atoms, like rubbing your hands to make heat. We have this incredible flow of energy in our walls, just waiting to be used. But how do we control it? We tell electrons when to flow and when to stop with a humble switch. Off means a physical gap, like raising a drawbridge. Electrons reach the gap and can't jump it. On closes the path, the drawbridge lowers, and the circuit is complete. An uninterrupted superhighway lets the energy wave continue and your device springs to life. This complete path is a circuit. Electricity only does work when it has an unbroken loop. A big hole in the hose spills water early. The end never gets flow. Circuits are the same. Power must go out and come back. One prong carries electrons in, the other returns them. A third ground adds safety. Plugging in connects the device's wiring to the wall, closing the loop so current can flow, do work, and return. Flipping a switch or plugging in is you saying, "Okay, electrons, the path is clear. Go to work." Once the electrons enter an appliance, their journey gets really interesting. This is where their energy is converted into something useful: light, heat, sound, motion. Appliances are workstations with components. Many add resistance, so electrons give up energy to do jobs. In an incandescent bulb, a thin tungsten filament has high resistance. Electrons collide with atoms like crazy, generating intense heat, over 4,000 degrees, about 2,200 degrees C. It gets so hot it glows, producing light. In a TV, current powers processors, decoders, and feeds the screen. Thousands of LEDs shine at precise brightness and color to create the picture. In a fan, electricity in coils creates magnetic fields that spin a shaft, converting electrical energy to magnetic, then to kinetic energy. Every appliance cleverly converts electrical energy into light, heat, sound, or motion. We talk about electricity flowing into an appliance. So does the appliance use up electrons? Not quite. Like marbles in a filled tube, push in here, one pops out there. The tube doesn't consume marbles. Your lamp, TV, and refrigerator don't consume electrons. They consume the energy the electrons carry. The electrons continue on to complete the circuit. Electrons flow in on the hot, do work, then flow back on the neutral. They travel through house wiring, out to local lines, and back into the power grid, a continuous loop. Power plant to house to lamp and back again. The plant pushes electrons into the grid. The push eventually makes its way back. No loop, no current. Without a return path, electrons pile up and flow stops, like a traffic jam. The return wire is the way home, keeping electron traffic moving. Electrons are part of a vast, shared sea. The utility sells you energy, delivered by that sea, ready at a switch. From the tiniest restless electron to the vast power grid, electricity is a story of connection and flow. Inside silent wires, a hidden dance unfolds. Wires are superhighways packed with mobile electrons, ready to move. A switch is a gatekeeper that opens and closes the path for energy to travel. Flip the switch, and a near-instant chain reaction starts miles away and finishes with work at home. Think marbles in a tube or water in a hose, a wave of energy passed along trillions of particles. Appliances resist flow just enough to convert energy into light, sound, cooling, or motion. Devices consume energy, not electrons. Electrons pass through and return to complete the loop. From generators to transformers, from copper conductors to insulating jackets, the system delivers energy safely and efficiently. A monumental feat we rely on every day. Next time you plug in or turn on a light, consider the invisible world you command. A sea of electrons waits in the copper, ready to unleash a wave of energy. It's not magic. It's really cool science happening all around you. And now, you're in on the secret.